Okay, so we have Professor Ryan Vinroot, and he's going to give two lectures on real representations for finite groups of Lie type. Ryan, over to you.
Thank you, Anupam. Thank you very much. Of course, when all of this started, when we started talking about this, I was looking forward to visiting India again. But this is good as well. You know, we're not in the same room, but maybe at the next one we will be. So thank you very much for having me as a speaker. I'm going to share notes now that I'll also email these to Anupam and Shripad to make available. So let me share. So as is reflected in the title, this pair of talks will be about real representations of finite groups of Lie type. I know the first set of lectures was on representations of finite groups of Lie type, and so we will of course apply a lot of that theory that you've seen there. And in this first lecture, there are going to be some, well, introductory concepts. I've made some exercises, and in the second lecture, we'll get into a lot more detail. And I think with the exercises, we'll all be on the same page for the second talk. So I'd like to set up the main question. So let's begin with just a finite group, G. And we have an irreducible complex representation. Pi is a representation, V is the space, and pi has some character chi. So this chi might be real valued. You take the trace and you might get all real values. So the question is, if you have a character which is real valued, when can that be realized by a representation that is also real? That is, in terms of matrices, when can we find a basis for a vector space V so that the resulting matrix representation is all real entry? So when is this possible? Just because the irreducible character is real valued does not mean the resulting representation can be realized over the real numbers. There's a very small counterexample. The 2 group, the quaternion group of order 8, there's a dimension 2 representation which is real valued, and there's no basis for which the representation can be realized over the real numbers. So both things happen. It might be a real representation, it might not. So a long time ago now, I think this qualifies as an old paper from 1900. Frobenius and Schur, they gave an answer to this with an invariant. So given our representation pi with character chi, if one computes the sum over all elements in the group of chi of the square and then average that over the elements of the group, this is an invariant of this representation, and it only takes 3 values, 1, -1, or 0. And it tells you, 1, exactly when the representation is a real representation, -1 if the character is real valued, but the representation is not a real representation, and otherwise 0, that is if chi takes values that are not real. So this is called the Frobenius-Schur indicator, or just the indicator. And the nature of the character formula is such that we can get a nice formula using the orthogonality relationships of irreducible characters of finite group. And if we look at the sum over all characters, one can do this as a first exercise. There'll be a more general exercise later, but this comes from the orthogonality relations. If one computes over the sum of all irreducible characters of the group G and multiplies the degree of that character by the indicator, that's always equal to the number of elements in the group which square to the identity. So this is a very nice combinatorial statement, especially if one can count, and that will be important if one can count the elements in the group which square to the identity. This tells us something. So this will be very important for some of the things we'll look at. So another standard result in character theory that maybe many of you learned in your first character theory course on finite groups. If you look at the number of real valued irreducible characters of G, so you look at the character table, you look at all of the columns of the characters which take only real values, the number of such irreducible characters of G is always equal to the number of conjugacy classes of G, which are so-called real conjugacy classes. These are classes which contain elements that are conjugate to their inverse. And so this has very much to do with the fact that if you look at chi of G inverse, that is just the complex conjugate of chi of G. And chi, irreducible characters, are invariant on conjugacy classes. So one can count off the number of real valued irreducible characters by counting the real conjugacy classes. And this prompted a question of Brouwer. So in 1963, Brouwer wrote a paper with a lot of problems on finite group representation theory. And if you ever are looking for a problem to work on, looking at his paper is a great one to look at and to do some research to see many of them are unsolved. But this happens to be the fourth problem in Brouwer's 1963 paper. So Brouwer asks, if you have a finite group G, what's the number of irreducible real representations of G in terms of some group theoretic data of G? So that is the number of real valued irreducible characters is the number of real conjugacy classes. So we just need to understand just group theoretic properties of G to understand the number of real valued characters. But some of these real valued characters correspond to real representations. How many of them in terms of, say, conjugacy classes or something of the like? So this is a wide open problem. There's some argument that there may not even be a good answer for finite groups in general. In the second lecture, we'll talk about a few general results for finite groups, and especially things get wild for two groups. So this just appears to be a somewhat intractable problem unless you restrict your class of groups, finite groups that you're looking at. So the main point that we're trying to get across here in these lectures is that maybe there is a very nice answer to this problem for finite groups of Lie type. Maybe we can say exactly how many real representations there are of a finite group of Lie type in terms of group theoretic data of our finite group of Lie type. This seems plausible. Still, we're a far way off from answering this, but one of the things I'd like to do is convince you that this is a very real possibility, no pun intended. Okay, so, well, this question seems to be a hard one. Here's another question that's related to it. If we're given a finite group G, well, before I read the sub-question, we can tell when a finite group G has all real valued irreducible complex characters because we can look at its conjugacy classes and determine whether all of the conjugacy classes are real conjugacy classes. If they are, all of its irreducible characters are real valued. So we could ask, if we have a finite group, how do we tell whether all of the irreducible complex representations are real representations? This is another question, which seems difficult. There are partial answers. But in general, it seems difficult. But one of the things we'll see is that there seems to be possibly a very nice answer for this for finite groups of Lie type. So just to back up a minute, what we're asking in this problem is, when do we have epsilon chi, so this Verbena Schur indicator, which tells us whether a character comes from a real representation or not, when are they all 1? So these are either 1, -1, or 0. When are they all 1? When they're 1, we say the group is totally orthogonal. Where does this come from? So this implies some sort of geometric properties. So there is a nice geometric interpretation of the Verbena Schur indicator. And let me say a few words about that. Well, let's suppose we have a finite group and we have an irreducible complex representation with character that is real valued. So pi may or may not be a real representation. So we're about to have our first exercise that that will be your homework before the next lecture. So if you have a real valued character, then the representation corresponding to it is self-dual. That is, the character being real valued is equivalent to the representation being isomorphic to its dual representation, its natural dual representation. So this is a canonical action on the dual vector space. And if this is true and pi is irreducible, well, we have something about irreducible representations of finite groups through Schur's lemma. And there is a way of unwinding the intertwining operator between these representations and using the definition of the dual vector space to translate this into saying that there is a bilinear form on our representation space V to the complex numbers, which is unique up to scalar. So this part comes from Schur's lemma, and which is G invariant. So this is our first exercise. This is a good exercise to translate this pi being isomorphic to its dual and taking that statement and using the fact that pi is irreducible in Schur's lemma to show that there exists a unique up to scalar multiple bilinear form with this property. Well, we can be a little sneaky and we can say if we interchange the variables, if we decide to define b tilde to be just b but the variable switched, this is another such bilinear form with this property. Okay, fine. So that means b tilde is a scalar multiple of b, but then we can switch the variables back. B tilde tilde, say. But then b tilde tilde is just b again because we've switched the variables twice. And that means that alpha squared, our scalar, that comes from this uniqueness up to scalar, alpha squared b is b, which means this alpha, which tells us how switching the variables is related to our original form, this alpha must be plus or minus 1. And it turns out that from the work of Frobenius and Schur, this alpha, this scalar in front, is exactly the Frobenius-Schur indicator. So what does this mean? This means if we start out with a representation that is self-dual, that is the character is real valued, then the indicator is 1 if and only if this b is symmetric, right? If b tilde is equal to b, then that means it's a symmetric form. And it's minus 1 if and only if b is skew symmetric. That is, we have a minus sign if alpha is negative 1. So this tells us something about the nature of our representation space. This says that the indicator is 1 exactly when we have a representation where the image sits inside of an orthogonal group because the image is leaving this form invariant. And the indicator is minus 1 if and only if the image under our representation sits inside of a symplectic group defined by B, because then this form is skew symmetric and G, again, it's invariant under G. So this is where these geometric names come from, these situations for a self-dual representation. Either pi is orthogonal if the indicator is 1, or it's symplectic if the indicator is minus 1. So now this is why we call a finite group such that all of its irreducible characters have Frobenius-Schur indicator 1. We call this a totally orthogonal group because all of its irreducible representations can be realized as representations that land in an orthogonal group. So this has a very, very geometric significance in terms of the nature of the representations of the group. And so here's kind of a philosophy for why this is even a series of talks. We have this very nice geometric nature of Frobenius-Schur indicators. And these indicators tell us some geometric nature of the group, So if these groups are defined geometrically as our finite groups of Lie type, then it stands to reason that there should be some nice answer as to whether these Frobenius-Schur indicators have some nice group theoretic description in terms of the, say, the conjugacy classes of the group. So this is the reasoning for why maybe there is a nice answer to this question for finite groups of Lie type. Okay, so this is the introduction. This is the main objects for the group. So far, we've only talked about finite groups. And so next, what I'd like to do is give some examples. So I claim there should be maybe a nice answer for these finite groups that are defined through some geometric significance. And so what I'd like to do first is look at Coccidr groups. So Coccidr groups, that is finite reflection groups, finite real reflection groups. These are finite groups which are defined to be generated by real reflections in some finite dimensional real space. Some of these are Weyl groups. This is the connection to finite groups of Lie type. Coccidr groups sometimes are Weyl groups of algebraic groups, and other times, well, there's a few cases where they are not, but this is all completely classifiable, and we'll say something about this. So first, the Coccidr groups, the finite Coccidr groups, one can classify them. There are irreducible Coccidr groups, and these have line up with a similar classification to groups of Lie type. They're type A, B, C, D that are infinite in series. There's G2, F4, E6, E7, E8, and then there are the non-Weyl groups. And the irreducible types are the dihedral groups. And then there's a few called H3 and H4. But most of them are Weyl groups. But the point, excuse me, the point is that the irreducible representations of all of them have been constructed. And when one constructs these irreducible representations, it turns out that all of the irreducible representations are real. They all have Frobenius-Schur indicator 1. And so all of these finite Coccidr groups are totally orthogonal. And well, I suppose it's not obvious. There's no nice universal proof. We'll say something about this. But in retrospect, one may not be surprised since these are defined at the beginning as finite groups generated by real reflections in a real space. But then we can take any irreducible representation of them. It turns out all of them are forced to be real representations. So this is only through the construction of the representations. This is the hardest way to check whether the representations, what are the Frobenius-Schur indicators of the representations of a finite group, go through the construction of all of them. This is the hardest way. But if you do it, you can get your answer. So all of these representations was completed in 1974. Larry Grove, who was actually a colleague of mine in my first visiting position in the U.S. For those of you who don't know me, my first postdoc was actually at TIFR many years ago now, and after that, I was at University of Arizona. Larry Grove was a colleague of mine at University of Arizona. So as I said, there's no known proof for this for all Coccidr groups. This is an open problem. If one of you had a proof, some universal proof for why a finite Coccidr group is always totally orthogonal, that would be extremely interesting. It's unknown. However, Springer gave a cohomological proof that if you have a Weyl group, then all of the irreducible complex representations are defined over the rationals, which is much stronger. That's a different question. But all of the Schur indices are 1. So we won't talk much about Schur indices, but that's a more general question. However, this statement is not true for Coccidr groups about being defined over the rational numbers. So this doesn't give a universal proof for being defined over the real numbers because this last Coccidr group, which is not a Weil group, is it has a representation that is not defined over the rational numbers. Okay, so we also have a meanwhile there is a paper of Carter from 1972 who proved that for any Weil group, every element can be written as a product of two involutions. So involutions, I'll just define to be any element which squares to 1, including the identity. I'll include the identity in this. So this is a property of Weil groups, and this actually does, one can check quite not well, it takes a little work, but one can check that for the other non-crystalline, that's just why I called them Weil groups, the non-Weil groups that are Coccidr groups, this also holds. So here's another exercise. This is a quick group theoretic exercise. If you have a finite group, then an element can be written as a product of two involutions in that group if and only if that element is conjugate to its inverse by an involution. So we call that, so something can be written as a product of two involutions. First, that implies that that element is conjugate to its inverse, so it's a real element. But something stronger is happening. It's a real element by an element which squares to the identity. So we say that a finite group is strongly real if every element can be written as a product of two involutions from the group, or equivalently, if every element is conjugate to its inverse by an involution. So what this is saying is every finite Coccidr group or real reflection group is totally orthogonal and strongly real. So all of the representations are defined over the reals, and every conjugacy class is strongly real. So another group theoretic exercise, this is a good warm-up problem. Everything in the symmetric group, you can check this by hand. Everything in the symmetric group is strongly real. You can write everything in the symmetric group as a product of two elements which square to the identity. That's a nice exercise. Okay, so this is a very nice statement. We have some property that is about the conjugacy classes here. Well, we're going to look a little farther into these Coccidr groups. So first, a parabolic subgroup of the Coccidr group. First, when you classify and define Coccidr groups, then one writes down the set of fundamental generators, which are fundamental generating reflections for that Coccidr group. And if you take any subset of those fundamental generators and look at the subgroup defined by them, that is called a parabolic subgroup. And so parabolic subgroups, you just take a subset of the generators, you generate the subgroup. This is also a real reflection group because it's generated by real reflections, fundamental reflections of the larger group. So this is called a parabolic subgroup, not to be confused with the parabolic subgroup of a finite group of Lie type. So, however, I'm bringing this up because in so-called Howlett-Lehrer theory for finite groups of Lie type, the normalizers of parabolic subgroups of these Coccidr groups play some significance in the representation theory of finite groups of Lie type. They are not themselves parabolic subgroups. The normalizer of, well, they are not themselves Coccidr groups, I should say. The normalizer of a parabolic subgroup. They have some other structure. They're more general. So, for example, here's an exercise. If you take the symmetric group, well, so the fundamental reflections are these fundamental involutions where you exchange 1 and 2, exchange 2 and 3, exchange 3 and 4, exchange 4 and 5. These are the fundamental reflections for Sn. So if you take a subset of those and see what is generated, you get a parabolic subgroup, and the normalizer of that parabolic subgroup turns out to be a direct product of wreath products. So this is another exercise in symmetric groups. So this itself is not a Coccidr group, but it is some product of wreath products of Coccidr groups. So as it turns out, these normalizers of parabolic subgroups inside of Coccidr groups, they also have a very nice property. And this is a result that is completely by exhaustive analysis. So there's no universal proof of this, but it also happens to be true. If you have a finite Coccidr group and you look at a parabolic subgroup, then the normalizer of that parabolic subgroup is also totally orthogonal and strongly real. So this is a result of Klaus Lux, Mandy Schaefer-Fry, and myself from 2012. And, well, the proof is for these infinite families of finite irreducible Coccidr groups, you go through the structure of these groups. For example, for the symmetric group, you have to understand Reith products, direct products, and one can get the information from that structure. There's a little more to do with type Dn because you have certain index 2 subgroups there. And then also dihedral groups. These are quick. Dihedral groups are quick. That's another good exercise, is to understand this for dihedral groups. But then for the finite Coccidr groups of these exceptional type, G2F4, E6, E78, H3, and H4, the proof was completely computational. And, well, these character tables are stored in GAP, so one can go through the character tables and check that, well, first go through, form every parabolic subgroup, form every normalizer over the parabolic subgroup, look at all of the irreducible characters of those, and then look at, well, you have to look at whether the conjugacy classes are strongly real. So how does one do that? This is also a very nice exercise, and if any of you are interested in the computational side of this problem, this is a kind of a fundamental statement. So this is how one checks computationally whether something is strongly real. So this is a general result for a finite group. If you have a finite group, you take 3 conjugacy classes you're interested in. So in this case, we're saying our elements in C3, if C3 is some conjugacy class and C1 and C2 are both classes of involutions, we're asking if elements in C3 can be written as products of one element in C2 with one element in C1 and one element in C2. So the number of ways in 1, 2, 3, this is the number of ways one can write a fixed element in C3 as a product of something in C1 times something in C2. So we're interested, if C1 and C2 are classes of involutions, we're interested in whether in 1, 2, 3 is 0 or non-zero. And it turns out this number is equal to this nice character sum. So this is another exercise. This one, you also use orthogonality of characters to prove this. So this is a finite group character theory exercise, but it's, as you can see, if one knows the character table of a finite group, we can just run through the character table and run through all of the conjugacy classes and check which things are strongly real and which things are not by running through C1 and C2, the classes of involutions. So let's go back for a second. We've got all of these examples, geometric examples, so finite Coccidr groups and normalizers of parabolic subgroups of finite Coccidr groups. These are all totally orthogonal and strongly real. And from this Frobenius-Schur involution formula that we looked at on the very first page, remember, the general statement was for any group, if you sum over all irreducible characters, the indicator times the character degree, you get the number of elements which square to the identity. So G being totally orthogonal is equivalent to all those coefficients being 1 instead of possibly -1 or 0. And so G being totally orthogonal is equivalent to the character degree sum being equal to the number of elements in the group whose square is 1. And, well, so I just wanted to mention that when one looks at the symmetric group here, we know exactly what these character degrees are. So the irreducible irreducible representations of the symmetric group are parameterized by partitions of the integer n. So you take a partition, one can write down, then there's many constructions of these irreducible characters. And one can parameterize the irreducible characters with partitions in such a way that the character degree of the character corresponding to the partition lambda has a very nice expression in factorial first over. So this is the product of so-called hook lengths. So if one writes down the diagram for a partition and one looks at every position in that diagram, one computes the hook lengths for each position. And if you take the products of those hook lengths and divide by n factorial, then you get the character degree. And so because Sn is totally orthogonal, this equality says that this sum is equal to the number of elements which square to the identity. Now, it turns out that this has an amazing combinatorial interpretation, and there's actually a very specific bijection one can make, and that is by restricting something called the Robinson-Shinstead correspondence. So this is, if you're interested in combinatorics, if you look at the Robinson-Shinstead correspondence and you reduce it to involutions, then you can get a very specific way of getting this equality, and therefore another proof that Sn is totally orthogonal. Another way, so this Sn and these, well, Sn in particular is a great example to look at because there are so many ways of proving that it's totally orthogonal. And so all of these different ways could be another tool to prove, to understand the Frobenius-Schur indicator of some other group, in particular, finite groups of Lie type. So another way one can prove Sn is totally orthogonal, or this method also works for these other Weil groups, type Bn/Cn and type Dn, is by computing generating functions. One for the character degree sum of Sn, which takes a bit of work and a bit of knowledge of symmetric functions, but one corresponds generating the generating function. I left out a word here. One corresponds the generating function for the character degree sum of Sn with the generating function for the number of involutions. So here's an exercise which this one is the first exercise, which is kind of fundamental to following the second lecture. And there's a lot of work with generating functions that we'll do in the second lecture. But so here's a nice warm-up exercise in generating functions. And that's that the number of involutions in the symmetric group, Sn, is exactly the coefficient of un in, might be the coefficient. I'm going to add a part to the exercise. Figure out whether it's the coefficient of u to the n or u to the n over n factorial. I believe it's the coefficient, now that I think about it, the coefficient of u to the n over n factorial of the expansion of the exponential of u plus u squared over 2. And then for type Bn/Cn, you look at the coefficient of u to the n of e to the 2u plus u squared. So you expand, say, the Taylor series of these things, and when you gather coefficients, correspond to that to a way of counting the number of involutions in these groups. And then through knowledge of the irreducible characters of Sn, one can also compute the character degree sum and correspond it to the same coefficient in this power series expansion of these exponential expressions. So this was some work of Jason Folman and I in 2014, if you're interested in finding that work. That's in Journal of Algebraic Combinatorics. Okay, so we're now going to move on to GLN FQ. So this was all kind of warm up, some families of examples of things where very nice things happen. And now we're going to work towards what's happening in our most nicely behaved finite group of Lie type, the general linear group over a finite field. Okay, well, I'd like to just jump right into the result, which I'm going to be discussing for the rest of the lecture, and will be the motivating example for the second lecture. So this result that I'm about to state, it's been proved again, and this is the nice thing about it, it's been proved in several different ways, so there are several different avenues for looking at other finite groups of Lie type. And in fact, for the results for other finite groups of Lie type, it's crucial that this has been proved in several ways, because we actually need several methods in order to get results for other groups of Lie type. So this was Rod Gow, who's now retired, but it was in Ireland. Clacherko, I believe, he was in eventually Clacherko was in Turkey. I believe he was in Russia at the time of writing this paper. And well, there were some errors in it that were later fixed by Inglis and Saxel. But then this was also proved in another completely different way by I.G. MacDonald in the second edition of his book on symmetric functions and Hall polynomials. So here's the theorem, which is somewhat surprising. So if you have a power of a prime, any power of a prime q, then, and you look at G to be the finite general linear group over FQ, the sum of the character degrees of that group is equal to the number of symmetric matrices in the group. So this is somewhat surprising to me. It still is. I find it very interesting, but I'd like to take some of the mystery out of it, and of course, then look at how this is proved in a couple of different ways. So one, it's not the number of involutions. We're not saying that this group is totally orthogonal. It has some other property. The sum of the degrees is the number of symmetric elements in this group. Okay, so, well, what's happening? So this is I'm letting transpose act on the left. So capital TG is the transpose of G when one views it as an element in GLNFQ. So first, one of these methods of Clacherko, extremely interesting, could be a series of talks on its own. So Clacherko, I'll just say a few words about it because we won't be able to use it. It doesn't extend to other types very easily, but Clacherko constructed the irreducible representations of GLNFQ in a very specific way. Clacherko constructed a series of subgroups and linear characters of those subgroups so that when you induce them, you get every single irreducible representation appearing in one of those induced representations exactly once. So one constructs this sum of irreducible characters as a representation. So this is called a model for a group when one constructs the multiplicity-free direct sum of all irreducible representations. One constructs that in some explicit way. So Clacherko does this as a direct sum of induced linear characters from subgroups. And so one can find the degree of that. And when one finds the degree, it turns out to be the number of symmetric matrices. But this is difficult to do. And as I said, this doesn't extend to other types very easily that anyone understands very well yet. So I'll simply mention that and encourage you to go read something about it because it is very, very interesting proof. But we're going to move on from that proof because, as I said, it doesn't help us too much in the broader question for finite groups of Lie type. Okay, so first I'd like to focus on Gall's proof. partially because Gao was able to extend his method to some other types of groups of Lie type. Okay, so what does Gao do? So instead of looking at the finite group of Lie type GLNFQ, he extends it by a semi-direct product. So we're just going to look at a group that is a degree to extension of the general linear group by the inverse transpose automorphism. So inverse transpose, this is an automorphism of the general linear group. And geometrically, it's a very important automorphism. It comes from a graph automorphism of the general linear group. And what that is an automorphism which on the Dinkin diagram for the Weil group, it's a specific symmetry of that Dinkin diagram. So the inverse transpose automorphism comes directly from, and there's geometric significance here, it comes directly from the graph automorphism of the Weil group, which is the symmetric group, which we've seen is very nice in terms of all of these properties. So really what Gao did was proved when Q is odd. Now we're going to, one drawback of Gao's proofs is that it only works for Q being odd. And one of the things I'd like to explain is why his proofs only work for Q odd. And then we'll bring in a method that works for Q, any Q regardless of parity. So what Gao did was prove that this extended group by an by an order 2 automorphism, that this group is totally orthogonal. So what I'd like to do is make a connection between this extended group and this result on GL and FQ. So what is the connection between this slightly bigger group being totally orthogonal and that group being having this property with the inverse transpose automorphism? So the best way to understand it is through something called a twisted Frobenius-Schur indicator. So the twisted Frobenius-Schur indicators, these things were developed, well, after Gao's paper. These were developed later. Gao didn't exactly invent them, but went through the mechanics of them. And then Kawanaka and Matsuyama were, I think, inspired a lot by Gao's work and were able to kind of generalize this construction. So let me say something about the twisted Frobenius-Schur indicators of a finite group. So we start out with a finite group, and we're going to take an automorphism which squares to the trivial automorphism. So this might be the trivial automorphism. When iota is the trivial automorphism, we'll see that this reduces to the standard Frobenius-Schur indicator. Okay, so we have a finite group. We have an automorphism which squares to the trivial automorphism. And we're taking an irreducible complex representation of our finite group with character chi. Okay, so here is another character invariant, epsilon iota chi, and it's the sum over all elements. And instead of chi of g squared, we're looking at chi of g times iota of g. So we hit one of these with our order 2 automorphism. And I'll also write this as iota upstairs, kind of acting in a pre-exponent here. So this is, so note when iota is trivial, this is just the Frobenius-Schur indicator. This is just chi of g squared. So it turns out that this indicator, Kawanaka and Matsuyama, proved that this indicator also only takes values 0, 1, and -1. And here is when it takes these values. So first, just some notation. If we have our irreducible character chi and we hit it with iota inside, that is, we compose chi of iota of g, this we'll call iota chi. This is also an irreducible character of G. This is just taking inner product, quick computation, small exercise. And so here is it's a little longer explanation because we're twisting by something. So epsilon iota of chi is 1 exactly when there's a basis for our representation space so that the resulting matrix representation has the following property. So here we're looking at the matrices with respect to our basis B. So if you look at the matrix for pi of iota G, this is the same as if you just conjugate all of the complex conjugate all of the entries for the matrix for pi of G. So again, it's important to realize here, if iota is the trivial automorphism, then this side is just pi of G and the matrix for that. And then we're just saying that pi of G is a real matrix, right? Pi of G matrix is the same as the complex conjugate of pi of G matrix. But here on one side, we're twisting by iota. Well, it turns out this, and this is true. That implies that the character values of iota chi, that is, if we twist by iota, is the same as chi bar. But just like in the real valued character case, these characters can be equal without there being a basis that realizes a matrix representation which forces that. So this is really the same situation as the standard Frobenius-Schur indicator, except we're twisting by iota on one side. And so this just makes it a little more awkward to state what's happening. So the point is that we have an indicator of -1 if these characters are equal, but there is no basis such that this matrix representation equality holds. And 0 if these characters just aren't equal. Chi twisted by iota and the complex conjugate of chi. So as I've mentioned as going through this, if iota is the trivial automorphism, then this is just exactly the standard Frobenius-Schur indicator. Okay, so now this is a real exercise, but more general than the first one that I gave, the first page. So we also have this equality, this nice formula. So for any finite group, if we have an order 2 automorphism iota, so again, use the orthogonality of characters, but the sum over all irreducible characters chi of G of epsilon iota chi, this twisted indicator times the degree, this is equal to the number of elements in the group such that iota of G is G inverse. Okay. Now, just like the standard Frobenius-Schur indicator had a geometric interpretation in terms of bilinear forms, so does this one. I don't particularly need it here, so I'm leaving it as an exercise to develop what this should be in terms of bilinear forms on our underlying representation space. So go back to what it meant for Frobenius-Schur indicators and reinterpret that with a twist on one side and interpret what that means in terms of bilinear forms. That's a good exercise. Okay, so once we understand this twisted indicator, which, as I said, Gal had to kind of develop the mechanics of it on his own, and later, you know, we now have the mechanics independently. The important order 2 automorphism here is exactly the inverse transpose automorphism. So we're taking iota in this situation where G is the general linear group to be the inverse transpose automorphism. And then what does this mean? This equality that the sum of the degrees of the general linear group is the number of symmetric matrices. Well, this statement is the same as iota of G is equal to G inverse. And from this twisted involution formula, This statement is equivalent to all the twisted indicators of GLNFQ being 1. So really, what's happening, this character degree sum being the number of symmetric matrices, this is equivalent to all of these twisted indicators for the general linear group, where we twist by inverse transpose. All of those are equal to 1. Okay, well then there's the matter of what was the proof. How does one use this extended group by the inverse transpose automorphism? And again, I'd like to go through a few details of this simply because it's crucial that while Gauss' method extends to some other finite groups of Lie type, it does so only for Q odd. Only for Q odd. And I'd like to make clear why that's true. There's actually a very interesting reason why the method of proof only works for Q odd. Okay, so how do we relate this statement that the twisted indicators are all 1 for the general linear group to, remember I stated the result that Rod-Gau proved was that this extended group was totally orthogonal. Okay, so here are some facts that kind of put all of this together. So first, if you have an irreducible character of this extended group, so general linear group sits inside of this with index 2. So first, every irreducible character of that extension is coming from the general linear group in one of two ways. Either you take an irreducible character of the general linear group, you induce it, and it is irreducible. That's possible. And that happens if and only if, I have to be a little careful here. This is I'm going to submit a few. So this is actually, there should be no conjugate here. I've just realized this. I'll submit, and this is a crucial error here. This is if and only if iota of chi is not equal to chi. And otherwise, if that is reducible, then it is a direct sum of two irreducible characters of this group that is contains the general linear group with index 2. And so all of these appear either as irreducibly induced or as a direct sum of two things that is coming from an induction from the general linear group. And then we can characterize what's going on with the indicators. Either, so using character formulas for these indicators and twisted indicators, we can relate either if this is irreducible, either the Frobenius indicator of that is the sum of the standard indicator and the twisted indicator of chi, or if we induce and we get these two things, the sum of these two things, the sum of the standard indicators of C1 and C2 is the indicator for chi and the twisted indicator for chi. So then what happens with these two equalities, if we have iota of chi is chi bar for all irreducible characters chi of g, that's equivalent to iota g being conjugate to g inverse, and everything is real valued in the larger group, then with all of that information, if the larger group is totally orthogonal, then one gets that all of the twisted indicators of the index 2 subgroup are all 1. And as a bonus, one gets that if you have a real valued character of the index 2 subgroup, then those have Frobenius indicator 1. So actually one of the things one gets out of this, which you can get in a more direct way, is that the general linear group is not totally orthogonal. However, all of its real valued characters are orthogonal. It has characters which are not real valued, but the ones that are real valued are orthogonal. Okay, so we got into the weeds a little bit here, but one thing to note, when iota is inverse transpose, this statement that all of these characters for the general linear group satisfy iota chi is chi bar, this is just equivalent to G being conjugate to its transpose. This is a linear algebra result over any field. This is always true. So this is something that you may have done when you learned about the Jordan canonical form for matrices to prove that every matrix is conjugate to its transpose. In fact, it's conjugate to its transpose by a symmetric matrix. So something even more. Somehow it's some kind of strongly real statement, but strongly twisted real, something like that. Anyway, Gall managed to prove that in the extended group, this group where we take the general linear group, we throw on inverse transpose as an order 2 element, we take the semi-direct product. Well, this is equivalent in the general linear group. If you're over any field and you take any element, then there's an element which squares to 1 such that U, G, transpose U is transpose G. So it turns out that this is the same as everything in G plus is real. This is an exercise, again, a purely group theoretic exercise. So if this is true for GLN, and if you look at this group that is a factor of 2 larger, then that means everything in this is real. Okay, so this is a little bit of technical business, some technical linear algebra, but these things are true. Okay, so now how does one show this is totally orthogonal?
So this
Yes.
G plus also this is strongly real? No, just real.
Pardon me? What's the question? G plus is?
Is it strongly real? G plus?
Yes, it is strongly real. Yes, it is strongly real. And in fact, not only is everything, yes, this is a good question. So this actually implies that this group is strongly real. Thank you. So not only does it imply that everything is conjugate to its inverse, but everything is conjugate to its inverse by an order 2 element. Thank you. So it's strongly real, and we want to show that it's totally orthogonal. So, okay, how does Gall do this? He uses an extension of Brouwer's induction theorem on characters. Brouwer's induction theorem, this actually is very interesting. The Brouwer's induction theorem was originally proved to use to show that all of the L functions of number fields were meromorphic. This had a number theoretic application to begin with, but the statement is of Brouwer's induction theorem is just if you have a finite group, any irreducible character is a z-linear combination or a generalized character, z-linear combination of induced linear characters from so-called elementary subgroups. So here's the generalization. This is called the Brouwer-Berman-Witt or Brouwer-Witt-Berman. I'm not sure the order of the names, how it should be. So this has to do with if you take any subfield of the complex numbers, how do you express the k-valued characters of that finite group? And the statement, well, you have to give up some strength of the Brouwer induction theorem. Any k-valued character is, again, a z-linear combination of induced characters, but these induced characters are not necessarily induced from linear characters. They're just induced characters from so-called k-elementary subgroups. I've wondered whether this can be applied to get some information on the L functions of number fields, and apparently it can. I asked. I've never gone back and looked through it, but this can somehow have nice number theoretic applications as well, like Brouwer's induction theorem does. But anyway, the main point is that if k is r, this is what we're interested in, the real valued characters. And if k equals r, the important subgroups here are called R elementary subgroups at 2. This is what they are. So an R elementary subgroup at 2 of a finite group is a semi-direct product of a cyclic group of odd order with a 2 group, where this 2 group acts on the cyclic group as follows. It either conjugates A to itself or its inverse. So B is in what's called the extended centralizer of A. It doesn't centralize A. It either sends A to itself or its inverse. So this is an R elementary subgroup at 2. And through general character theory and some work, one can show that for any irreducible character of a finite group that is real valued, there's a maximal R elementary subgroup at 2, M, and some irreducible character of M that is real valued, so that the indicator is the same. So in other words, what we're doing is we're going down if we want to know something about the irreducible character of our finite group. And it's for being a sure indicator, we can go down to some maximal, so-called maximal R elementary subgroup at 2. Okay, and I don't want to say more about these, except for this is the crucial point. Included in these R elementary subgroups at 2, and the maximal R elementary subgroups at 2, include Celof 2 subgroups. So when A is just this element of odd order, if this is trivial, and B is a 2 group, the maximal ones include the Celof 2 subgroups. This is exactly where we have to take Q odd in this argument. When Q is odd, well, the R elementary subgroups at 2 have very nice structure, and one can write them down. It's a long process to go through all of them and say, okay, well, these are all of this structure. There's a bunch of wreath products, and one can understand that they are totally orthogonal, the maximal R elementary subgroups at 2. However, when Q is even, the Celof 2 subgroups of this thing has as an index 2 subgroup the maximum unipotent subgroup of the general linear group, or the unitriangular group. These subgroups that have 1s on the diagonal and anything above the diagonal. So the maximal unipotent subgroup of GLNQ plus another order 2 element on top of it, because we're in G+. And the point is, the representations of these groups are completely intractable, somehow provably intractable. It's somehow, and I don't understand this statement, but it is. I have a colleague, Nat Thiem, who studies these representations, and these are in terms of the standard complex representations of these groups, in particular the Celof 2 subgroups of GLN FQ, where Q is a power of 2. It's completely hopeless to understand all of the irreducible subgroup, all of the irreducible representations of that group. What this means is that when Q is 2, this method completely does not go through. It just doesn't. You hit a group and you can't understand it, and instead of having you somehow, this method gives you subgroups which are harder to understand. Whereas when Q is odd, it gives you subgroups which are easier to understand, and one can give an inductive argument and get that the group is totally orthogonal. So when Q is odd, Gao manages to go through all of the maximal R elementary subgroups at 2 of this group, give a beautiful inductive proof that everything is totally orthogonal. So the large thing is totally orthogonal. Therefore, all of the twisted indicators are 1 for the smaller group. And, well, the nice thing is that this method goes through for other groups when Q is odd. So in 1985, Rodgal used the exact same method, that is, R elementary subgroups at 2, inductive argument, to show that when Q is odd, the orthogonal groups over a finite field are totally orthogonal, which is convenient. They're orthogonal groups. They are totally orthogonal. They also are strongly real, even when Q is even. And then the special orthogonal groups, I'll say more about this in the second lecture, but the special orthogonal groups are, well, in dimension 4, they're totally orthogonal. I've left out an odd dimension, they're totally orthogonal when Q is odd. And when the dimension is 2 mod 4, the real valued characters are all orthogonal. And in the symplectic case, if you have a real valued character, then the character is orthogonal if and only if the central character is trivial. Now, there's more to say about this as well, which I'll say more about in the second lecture. But the point is that when Q is odd, we can, Rodgal got these very nice, very general statements for orthogonal and symplectic groups when Q is odd. Okay, so this will place some more significance in the second lecture next Saturday. Okay, so now I'd like to go back and look at a second proof of this statement for the general linear group. Because in the second lecture, what we have to do is combine the results of Gao with some variation of this generating function proof. So this is a variation on MacDonald's proof in his book on symmetric functions and Hall polynomials. So the main idea is to match a generating function, like I mentioned before for the symmetric group. So come up with a generating function for the number of symmetric matrices in the general linear group, and match that with a generating function for the character degree sum for the general linear group. So the question, of course, is, can we do this? If we can and match them, great, we have a proof. So first, we count the symmetric matrices. How do we count the symmetric matrices? Well, we look at the action of GLN on the symmetric matrices by this action of similarity. You take a symmetric matrix, hit it with G transpose on the left, G transpose on the right. What that does is really looks at the similarity classes of invertible symmetric matrices in the general linear group, and it looks at the classes when it looks at the classes of the non-degenerate symmetric bilinear forms on the underlying vector space. When Q is odd, there are two classes. Actually, whether Q is even or odd, there are two classes. But when Q is odd, the two classes have stabilizers, exactly the two types of orthogonal groups. And so you can just say, using this group action, the symmetric matrices is the number of symmetric matrices is the sum of the indices of these two stabilizers of the two classes under this action. When Q is even, things are a little different, not in a troublesome way. It's only the fact that symmetric matrices in that case don't correspond directly to quadratic forms. There's still two orbits, and one can still look at the stabilizers of those orbits, and you can still count them, and you still get the same expression. You just have to do it slightly differently. And one gets the same expression. And if one writes down the orders of these groups and looks at the indices and gets the expression, then you get this nice expression, q minus 1, q squared, q cubed minus 1, q to the fourth, and dot, 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 until you have n factors. So whether n is even or odd, you end with a q to the n minus 1 or a q to the n in this product. Okay. So here's now a more important exercise in terms of where we're going next week. So this expression for the number of symmetric matrices is exactly this times the coefficient of u to the n in this generating function. So if one expands this, so use geometric series, that sort of thing, expand it. So this is a little challenging. You need to know a little something about Q series, but it's a true statement. So if one takes the coefficient of u to the n in this, then we get exactly, well, if we then multiply it by q minus 1, q squared minus 1, etc., we get exactly the number of symmetric matrices. So this is some kind of generating function for the number of symmetric matrices in the general linear group. Okay, so this is counting symmetric matrices. There's some linear algebra. There's a little bit of combinatorics of generating functions. But now we get to the main point. Now we have to find the generating function for the character degree sum of the general linear group. Okay, so now we go back to what's going on with the irreducible characters of the general linear group, GLN FQ. And these things are parameterized by a pair. First, we take a semi-simple class of the general linear group. And then we look at the centralizer of the semi-simple element. We look at the unipotent character, a unipotent character of that centralizer. And that pair, semi-simple class and unipotent character, parameterizes an irreducible character of the general linear group. And there's a specific construction, and we'll see more of that next time. But this is, you saw the lectures of Dipendra Prasad on the representations of finite groups of Lie type. So there's a very general construction here, and corresponding the so-called Jordan decomposition of characters of finite groups of Lie type. But the point is, we can completely write this down for the general linear group. So the semi-simple classes of the general linear group, well, we're just choosing irreducible polynomials to some powers so that the product of all of them has degree n. This is a semi-simple class. You're essentially just choosing the eigenvalues and their multiplicities. Okay, great. So we know how to do that. And what are the centralizers? Well, the centralizers of these are not so hard to describe. If you have an irreducible polynomial of degree d, and it appears with exponent m in the description of the semi-simple class, well, the centralizer of that factor is a general linear group, GLM q to the d. And so this means the centralizer of our semi-simple element is a product of these general linear groups. We have a bunch of GLM q to the d's, where d is the degree of the irreducible polynomial. So in other words, the size of the Frobenius orbit of that eigenvalue, and m is the exponent to which that irreducible polynomial appears. What are the unipotent characters? Well, so now we're applying the knowledge from this course, the first course, and the unipotent characters of this centralizer. Well, it's a product of unipotent characters of these factors. And these factors, well, the unipotent characters of these are parameterized by partitions of M. So again, these things correspond to some symmetric group combinatorics. So if one takes a partition of M and one looks at, well, the unipotent character corresponding to that, we're not going to construct them. All we need is the character degree, because we need the character degree sum. So it turns out the character degree of the unipotent character corresponding to the partition lambda is given by, well, not a terrible expression. Again, we have a product over hook lengths. So this part you should think of as some sort of Q generalization of what we had for the symmetric group. This is some sort of Q generalization of n factorial, and we have a product over hook lengths again. And this thing, well, don't worry about too much about this. This is some power of q, and it's some statistic that, well, it'll go away in a second. So let's not worry ourselves too much about this numerator. But the main part is that we have this product over hook lengths, and we have this expression. Instead of a product of hook lengths, we have a product of q to the d times the hook length minus 1. Okay, well, this expression, this is where the magic happens. This expression, through well understood symmetric function theory of the symmetric group. So the crucial part here is that all of this depends on symmetric group combinatorics, which is well studied and well understood. And it turns out there's a symmetric function called the Schur symmetric function, which one can rewrite this expression in terms of, except, well, this factor. One can rewrite this expression in the following way. So some power of q, 1 over q to the dm, times this Schur function, where a symmetric function has an infinite number of variables. We plug in 1 over q to the d, 1 over q to the 2d, etc. So this part can be written purely in terms of a Schur symmetric function. And it's not too important what the Schur symmetric function is right now. The point is that we can rewrite this in terms of that. So I'm going to call this expression, this delta for degree. It's kind of a modified degree. We're leaving out this factor. And it depends on lambda, and it depends on d. And remember, lambda, the size of this partition is m. So this implicitly depends on m as well. But we have this partition on which it depends. Okay, so the unipotent character C of the centralizer is a product of those characters, and the character degree of chi of the general linear group, well, again, this is a very general expression we'll look at next time, again, coming from the so-called Jordan decomposition of characters, but it's the degree of that unipotent character times this other expression. So this is just the p prime factor of the index of the centralizer in G. And it turns out what happens here, this cancels out with a bunch of factors. And what we end up having is just a product of these Schur functions times this expression, except this expression is just from I equals 1 to n. So a bunch of things cancel, and we have a bunch of Schur functions, and then we have this. So what we're really doing is we're saying, okay, how do we get any character degree? We have a choice of semi-simple class. We have a choice of unipotent character. And this is kind of the this is the big exercise to understand before next time. Given all of this information, the sum of the degrees of the irreducible characters of GLN over a finite field with Q elements is exactly this. So this factor I'm saying is factoring out. This factors out. So this times the coefficient of U in this product. So what is this? So product as d goes from 1 to infinity. This is the number of degree d irreducible monic polynomials other than t, the polynomial t itself in FQT. So this is the number of degree d in FQT. And then this is our expression for the character degree sum. I'm sorry, for the character degree, modified character degree. And this is a sum over all possible partitions, lambda. So what you have to do is look at this and say, okay, how do we get a coefficient of u to the n? Well, it depends on a choice of irreducible polynomials and then a choice of partitions. Choices of partitions correspond to choices of unipotent characters. And so the thing to unwind here is that this generating function is exactly choosing to get a degree in term in the expansion is choosing exactly a bunch of semi-simple classes and a bunch of unipotent characters so that the corresponding choice sums to a degree in. So this is a big exercise, but it's an important exercise to move on from the general linear group. But the point is that these sure functions are so well understood and are so well studied. There's all kinds of identities, an unbelievable number of identities, really. And the point is that this generating function, which we can form from the knowledge of irreducible character theory of the general linear group over a finite field, this thing reduces from identities to exactly the generating function for the number of symmetric matrices. So the point is, if we know all of this character theory, and we can put all of this together, and then we know these identities, we can identify these generating functions, the sum of the character degrees, and the number of symmetric matrices. We can match them, and so they must be equal. This is true for every Q. And whether Q is even or odd, one thing I want to point out that is also crucial, this degree of unipotent character for the general linear group, this is true independent of Q. So this is true for any of these nice finite groups of Lie type. There's a polynomial expression for the degrees of unipotent characters in Q, and it is independent of what the Q is. That is crucial here. So this goes through whether Q is a power of 2 or whether Q is a power of any other prime. It makes no difference. And so putting all of this together, we match our generating functions, and we've accomplished this idea of saying, well, what if we could match these generating functions? We can in this case. Okay, so I'd like to stop there, and all of this we're going to, well, next time we're going to look at both the other classical groups of Lie type, and we're going to look at some exceptional groups, and we're going to look at more details of what's going on with the general character theory, the Jordan decomposition of irreducible characters, and how do you tell one is real valued from those parameters. So I will stop there, and I will turn it back to Anupam, I suppose.
Thank you, Ryan. If there are any questions, quick questions.
Beautiful talk, Ryan.
Hi, Dipendra. How are you?
Very good. No, I mean, you have packed a lot of material in one lecture.
Yeah, well, it's a Saturday. There's lots of time.
So, you talked about the character degree of unipotent representation. So there is some simple formula for that?
Simple, relatively simple.
For GLN.
For GLN, yes. And I think the crucial part here, let me go back to, so the crucial part, this expression, so the unipotent character is parameterized by a partition lambda. All one needs is the partition lambda. And if we get the hook lengths corresponding to that, just like in the symmetric group case, we take this product over hook lengths. We take this product that's some kind of Q factorial, and then this other data. This is just some data on the transpose of the partition. But yes, there's this very nice combinatorial formula for the degree of the unipotent character corresponding to the partition lambda.
Hello?
Yes.
In that formula, what was Q to the power di minus 1? What are those di's?
So D was, so we were looking at Q to the D. So,
Q to the power di. I thought it was di, not Oh, it is D times I.
D times I, correct. Yes, not D
Okay.
subscript I.
And
Yes.
Q to the power D is the cardinality of the field, Q to the power D.
That's correct. Yes,
Okay,
that's Q
okay,
to the power
okay.
D. Yes. And that came up because we were looking at the semi-simple classes. And so
Oh,
if you
so
have
the
some order D orbit, then the centralizer is a general linear group over Q to the D rather than Q.
so this dimension of the unipotent representation is very closely related to the Hooke length formula.
Very closely related, yes.
I
And in
mean,
fact, that's why we can do all of this and manipulate this, because it's so closely related to the symmetric group. And there's so many combinatorial things for the symmetric group, we can apply them all immediately for GLN once we can translate this into this symmetric group language.
okay, good. I mean, the other thing I was a bit unsure about the gauge proof about the sum of chi1 being the number of symmetric matrices eventually is quite elaborate. It's not simple.
It's not simple. No, it's not. It's not. But
It doesn't come by applying, so to say, Frobenius-Schur indicator and the twisted Frobenius-Schur indicator together, and then kind of some triviality, but you have to do a lot more work.
Yes, yeah, it's very involved. And you know, one of the things, so luckily for the general linear group there are other proofs, but the fact is, for the symplectic and orthogonal groups, it's the only proof of that I know of these computing these indicators. And yeah, I mean, one of the things I'm trying to get across is that this area is in desperate need of some new ideas to apply the geometry directly to get a statement about all of the characters. And as you
But the
know,
fact that GLN plus is totally orthogonal, that
yes.
is not difficult. No.
Well, it's difficult in that one has to go through all of these so-called R elementary subgroups at 2. I very much brushed over that because I'm not too concerned with that. I mean, one has to classify these so-called maximal R elementary subgroups at 2, and then go through all of them and say, okay, for each of these, we can see the structure is such that because of our inductive hypothesis, these things are all totally orthogonal. Therefore, the characters that correspond to the one for GLN plus, they have the same indicator. So it's quite a bit of book work. I mean, none of it is, once you have the method, it's a lot of book work basically. But it's purely group theoretic, in that one doesn't use the character theory of finite groups of Lie type in it. That's what I mean by that. It's purely group theoretic, and that it's just about the structure of the subgroups rather than the fact that it happens to be a group of Lie type.
Come on, beta. Very